This section provides a technical overview of AI agent frameworks and retrieval-augmented generation deployment. We are going to look at practical coding, deployment hurdles, and the regulatory landscape. Let's start with the fundamental coding task often seen in technical interviews: counting character occurrences and formatting the output. For example, if we want to process the string hello, the logic follows a clear process. First, we initialize an empty dictionary to serve as our key value store, giving us optimal lookup times. Next, we loop through each character in the string. For each one, we check if it exists. If it does, we increment its value by 1. If not, we add it with a starting value of 1. Finally, we output the result using f-string formatting. This allows us to cleanly inject variables right into the string, giving us readable results like h:1. Now let's look at the core RAG system in the top right. Moving from prototype to production introduces serious engineering challenges. First, we face data format changes. If your pipeline expects text PDFs and suddenly gets complex images, parsing fails. Second, policy updates like changing HR rules mean you have stale data, which often forces a complete re-indexing of your vector space. Third, there is technical debt. Library updates to tools like LangChain can change API signatures, causing runtime errors and latency. Finally, we have to worry about data leakage and memory limitations, which can expose sensitive information or result in incoherent multi-turn conversations if the agent loses context. So, how do we choose the right architecture? Let's look at the RAG versus fine-tuning comparison. RAG is generally much lower in cost because it uses existing models. It's incredibly efficient for data updates. You just swap or append documents in your database. On the other hand, fine-tuning is significantly higher in cost because it requires heavy GPU resources to actually update the neural network weights. Data updates are slow, requiring a full retraining cycle. However, fine-tuning does offer higher specificity for niche domains and styles. Finally, any deployment must navigate international regulations like the GDPR, the EU AI Act, and NIST standards. Compliance requires engineering teams to mitigate specific risks. These include jailbreak attacks where users bypass safety filters, hallucinations which are factually incorrect but confident statements, and prompt injection. Ultimately, the key takeaway here is that successful and responsible AI deployment requires mapping all these technical vulnerabilities directly to corporate compliance policies. Once these robust foundational safeguards are in place, we can begin designing truly autonomous agentic systems that can plan and execute actions on their own.
Let's dive into the fascinating world of agentic AI. At its core, agentic AI refers to an artificial system that operates as a truly autonomous entity. Instead of just answering a single prompt, the process follows a cycle. Given a specific goal or objective, the agent thinks ahead. It develops a structured plan of logical steps to reach that goal. Then, it executes actual actions based on those commands, like calling an API or searching a database. The beauty of this framework is that it operates with minimal human intervention, navigating the steps entirely on its own. Now, how do we actually build these? Over here, on the left, we have different architectural frameworks. LangChain is characterized by a linear, pipe-style structure, which is great for straightforward sequential pipelines. If you need more complexity, LangGraph utilizes a hierarchical graph structure with nodes and edges, perfect for workflows that need branching and loops. For multi-agent systems, AutoGen, developed by Microsoft, is incredibly powerful. It allows multiple agents to converse and solve tasks together. Similarly, Crew AI focuses on coordinating agents to mimic a real human workforce. Why is this so important? Well, Gartner forecasts that by 2029, roughly 80% of tasks will be handled autonomously. We'll see agents completely replacing traditional roles, where a backend developer agent writes the Python code and a deployment agent automatically handles the containerization. Let's look closer at the AutoGen framework, also known as AG2, right here in the center. To get started, we simply pip install AutoGen and import the conversible agent. AutoGen gives us four primary ways agents can interact. First is two-agent chat, which is just a direct back-and-forth exchange. Second is sequential chat, where agents are chained so one starts only after the previous one finishes. For larger tasks, we use group chat, where a manager agent coordinates a specialized team. Finally, there's nested chat, which uses conditional logic like these yes and no pathways to dynamically route the conversation. To make all this work, we have to configure our agents on the right side. Setting this up requires configuring the large language model. We need our API key in the environment and a configuration list that defines the model like GPT-4o Mini along with its temperature. When constructing our conversible agent, four elements are mandatory. First, we give it a name. Second, we provide a system message, which is basically the instruction manual defining its persona. Third, we pass in that LLM configuration list. And fourth, we define the human interaction mode. This interaction mode is crucial. The always mode forces the agent to pause for your feedback after every turn. Great for debugging. The never mode lets it run fully autonomously. And the terminate mode stops execution once a final answer is reached. Before you start building, beware of common pitfalls like missing API keys or omitting your config list or setting an invalid temperature. The ultimate takeaway here is that by combining a clear goal with structured LLM configurations, we can build specialized autonomous entities that coordinate to solve complex problems without constant human handholding. Now, speaking of those configuration settings, let's look at exactly how the temperature parameter influences the randomness of models' choices.
Now, let's talk about how we control the randomness of our language models. We use a mathematical parameter called temperature. Think of it as a dial ranging from 0 to 1. When we set the temperature to 0, the model's output is completely deterministic. It just picks the most likely next word every single time, giving us very repetitive and predictable phrasing like standard marketing tactics. But as we move this parameter closer to 1, we introduce randomness. The model becomes more creative and random, offering varied responses, like suggesting a cross-channel integration strategy. Next, we have multi-agent conversations. Imagine a scenario where a CMO agent and a CEO agent are talking to each other autonomously. We control these interactions with specific parameters. The role parameter tells us who is speaking. We use max turns to set a strict limit on their back and forth, which is crucial because it prevents infinite loops. If we set silent to true, it hides the messy intermediate dialog from our console. And finally, setting the summary method to reflection forces the LLM to synthesize a concise recap once they hit that turn limit. Let's look at what these agents might discuss, like a B2B versus B2C strategy. In our simulation, the CEO agent pushes for B2C, focusing on market demand and scalability for individual learners. Meanwhile, the CMO agent advocates for B2B, looking at higher revenue per contract. Through autonomous negotiation, they can actually converge on a hybrid approach. They might decide on an initial B2B focus to secure immediate revenue while simultaneously developing B2C channels. This really shows how well agents can simulate complex professional decision-making. Now, switching gears to architecture, let's talk about our vector database and metadata strategy. A vector database is built for vector embeddings. But here is a critical rule.
You should not use it for raw structured tables. Instead, it stores only metadata, like titles or IDs. The flow goes like this. A user asks a question. The system runs a similarity search to find the top relevant hits from that metadata. Then, our LLM uses that exact metadata to write a precise SQL query. Finally, it executes that query against a traditional relational database to grab the actual authoritative data. This brings us to the hybrid retrieval architecture. We are literally combining two systems. The vector database gives us fast, semantic lookups, it finds the meaning of the query, and the SQL database handles the exact transactional data retrieval. Together, they form a powerful hybrid system. For the vector side, you have options. ChromaDB is great for local prototyping on your own machine. Pinecone is a managed cloud service built for high scalability. And FAIIS from Meta is optimized for high-performance retrieval using GPUs. Finally, building all this is complex, so you need a debugging and implementation checklist. When things break, follow a systematic workflow. Always capture your error logs, use robust environments like Google Colab for line-by-line inspection, and absolutely avoid over-reliance on auto-completion because it hides the underlying logic. For implementation, ensure you extract embeddings properly. Configure your LLM to output valid SQL, validate that SQL, and continuously monitor your search parameters so your results are neither too broad nor too narrow. And that comprehensive approach is what allows us to build reliable, production-ready AI